Okay, hello everyone. So today we're going to continue our conversation around the concurrency and synchronization in LSTOR and continuing the 2VCC protocol that we had started last week. And if there's times, then we will move to the second concurrency protocol that have been studied and employed in the context of LSTOR, which is QCC or Quick. So kind of an overview, kind of a reminder of what we talked about last time is that the basic idea of the indirection, as we've talked about, is that we will turn our indexes from read indexes to lit. And the difference is that instead of directly pointing to the physical read of the record, we point to this stable read or this logical read. And from this stable read or from this logical read, we can actually find the latest version of the record. So that was the basis of the indirection, and also the idea that has manifested itself in LSTOR as just a column as opposed to being an independent data structure. So what we talked about says, well, what if we now distinguish between two kinds of read, a committed read and an uncommitted read? Committed one points to the committed version, the uncommitted one points to the uncommitted version. And so this allows already the read and write to kind of be rerouted, one toward what's committed, one toward its writing a new value or on the uncommitted segment. And so we said, once the transaction first writes a record, before marking it committed, it will be shown up in the indirection, in this extended indirection as the URID. And once it's committed, then the new version becomes the committed and the URID is set to null. We also said we can use this uncommitted location as an implicit indication of write-write conflict. We also mentioned that we can use this space also partially as holding a read counter, essentially a latch-free coordination mechanism that allows to keep track of how many outstanding reads are on the committed version. This read counter could either be encoded into the URID, or it could also be encoded in the CRID, or maybe both, in case that we have potentially many outstanding readers. So that would be another point of synchronization point that can be utilized in order to implement concurrency. So that's the basics. So that's kind of, so far we talked about the data structure. If we were to especially extended that indirection technique, what are the possibilities? And kind of exploring it from structure-wise and from how do you actually implement or realize a concurrency protocol. So now let's talk about the concurrency control protocol itself. And the concurrency control, which is the name if you're not familiar with, so any database concurrency is kind of goes on this subcategory of concurrency control. So that's the kind of the terminology that is used to refer to any kind of algorithm that allows synchronization and allows isolation of multiple transactions running together concurrently. So a revisit of two-phase locking, and that would be the two-phase locking would be the basis for the third milestone. Right now you have all the background and necessary tool to start your second milestone. And so now we make sure by the time you get to the third milestone, you also know all the necessary background information to be able to start that right away as well too. So two-phase locking, it has a phase of growing. So in this phase, you only acquire locks. And then once you acquire all the locks that you need, then you can start releasing them. So it follows by a shrinking phase. But the moment you start your shrinking phase, you can no longer go back and acquire a lock. And the intuition there is that if you've already released something and then you go back and try to gather it again, it is possible during the time that you had released it, something has changed and you won't be able to be aware of it. And so you will lose that, the isolation guaranteed. So then it is important that you have this growing phase. Essentially, by the time you finish your growing, you kind of mark your entire territory of isolation. So you say, this is my territory, nobody can really touch that. And it's sort of exclusive, almost. Logically, is an exclusive access that I have to it. But if you start dropping locks and try to release it, essentially, every time you drop it, once you have established this territory, you're essentially creating holes in it by dropping that lock. And if you try to acquire it again, well, again, you've already caused a leak in your isolation, and you won't be able to guarantee serializability anymore. So serializability is only guaranteed if you follow the strict two-phase of growing and shrinking, acquiring and releasing. So now, again, we have two types of lock. Generally speaking, we're going to add a third one, but normally we talk about exclusive lock or write locks, and then shared locks or read locks. And again, they are referred to differently in different database systems, and so both terminology is used. So we kind of use it interchangeably here as well too. And the exclusive lock is, as the name suggests, is it gives you full exclusive access. So it really eliminates any concurrent access to the data, while the shared lock, since it's the reader lock, multiple transaction can read the data without interfering with one another because they're simply reading it. So now we talked about, and that's where kind of we stopped last time, is that we say, well, what if we imagine a slightly different model? And in this model is we add a certification phase. So extending the 2PL with a certification phase. And actually the idea of adding certification is something that was first pointed out and discussed in late 80s. But now we're kind of take that idea and extend it in the form of 2VCC. But the theoretical underpinning of it can kind of go back to that extended 2PL model with certification phase. So with this certification phase, the basic idea is, as opposed to acquiring exclusive locks at the beginning, both the readers and the writer just simply acquire shared lock. And once the transaction completes its acquiring phase, once it acquired all the locks, it completed all the operation that need to be done, and it is ready to sort of commit the transaction to finalize the changes, make them visible to other transactions, then it enters the certification phase. And the certification phase, basically, it does what you would expect to be done initially, meaning it certifies all the rights, and it certifies all the rights by acquiring an exclusive lock or upgrading that shared lock to an exclusive. So that ensures that the transaction has exclusive access to these records in a sense of be able to writing it without violating the repeatability read of any other concurrent transaction. Because before acquiring an exclusive lock, the transaction already holds a read lock on it. So it's already certain that no other transaction could have overwritten what it has read so far. But now it also needs to ensure that it's not going to overwrite anything that any concurrent transaction that has already read. So, and that's the certification phase. So certifying, ensuring that these rights can go through, the transaction can be committed because there are no outstanding transaction currently that still reading the older version of the record. the currently committed version of the record. So once the locks become certified, then again, we kind of go back to the previous scenario, is that we enter the shrinking phase and they can be released. So let's pause here and see if there are any questions at this point.
I have a quick one.
Sure.
During the certify phase, are you like analyzing serializability of the transactions that have locks at that point?
So there's no analysis really need to be done. All of it is actually being carried out by the simple action of upgrading the lock from the shared to the exclusive. Because if you're able to upgrade the shared lock to the exclusive, in a sense, it could be kind of thought about that the transaction really started at the certification phase. And you would have been identical in the case as if you, right from the beginning, you got your certification lock, you got your exclusive lock. So you essentially, by certifying it, you now turn this into the 2PL. So now essentially becomes just your standard two-phase locking protocol. And the benefit is that instead of holding this exclusive lock for the entire lifetime of that transaction, you only limit that exclusion to just that certification. And that certification is literally as fast as locks can be acquired and basically released. It no longer involves any computation, any other operation that was needed to figure out, for example, what the value that you wanted to write, what value to read, go through all the indexes. So a lot has been done. So all of the actual work of the transaction is already completed. And while we did all the work of the transaction, we did not prevent others to continue reading the data that we are eventually going to write to. So in a sense, as long as we haven't got to the certification phase, this transaction hasn't really been ran in a sense. And so it's anything that is ongoing and it's conflicting, it's going to be serialized before this particular transaction can be certified. So that's sort of the general intuition. And it is optimistic in a sense is because it assumes implicitly that if there were any concurrent reads that were reading the data that I'm eventually going to write, by the time I get to the certification phase, they have already completed. And so on that optimistic ground, my certification will smoothly pass and everything will be as expected. Of course, it's possible during the exclusive during this certification, deadlock is possible. So that's a possibility. Also, it's possible that the locks that I want to acquire to get to the exclusion, they're currently not available. And then we're left with two choices there. We could either wait till they become available, or we could simply just abort. And so we have that choice as well too. Then turning it into either a blocking or a non-blocking protocol. Any other question? So, yes.
Oh, I was just gonna ask to see, to just like clarify, if I like understand this correctly. Like there would be many transactions occurring at the same time, and with this model, we're allowing them to all read simultaneously, and then it gets to a point where it's the certification phase, and then at that point we would only upgrade the locks on the ones which we choose to write to, and at that point we're assuming that the read-only transactions would have completed by now. Is that right?
Yeah, so yeah, I think you kind of summarizing, touching the key important points there. Yeah, so in the beginning, so normally the transaction will have will have a mix of, let's say, read and write, put the read-only transaction on the side, but the transaction, like normal transaction, would have few writes and few read operation. So with the 2PL, well, we will require both the read and write operation as we going through these operation one by one. So for each transaction, maybe I do some read, then I will do some write, then I do more reads, and maybe I do some more writes. And if I'm doing multiple transactions at once, each of them kind of do some read and writes. And in the normal 2PL, before you read something, you will get a read log. Before you write something, you get a write log. And so that would be the normal 2PL. But in this new model, we're saying, even if I want to write something, I'll just get a read log on it initially. And the writes that I'm going to write, I'm not going to actually write it yet to the data. I may just write it locally in my buffer, or just locally, not into the database itself, not into the table itself, for example. So I do my writes like locally. I kind of keep my writes to myself, and then I'll keep my write to myself, and I only hold the read logs on both that I'm planning to read, and also on those that I'm planning to write. And once I get to the certification phase, well, I've already have read logs on everything that I need, everything that I've read, and I also have read logs on anything that I want to write to. So then the certification phase simply says, well, for all those records for which I already have a read log, and now I wanted to write to it, I need to certify it, meaning I need to upgrade my shared log or my read log into a write log or an exclusive log. So that becomes a certification. So by the end of the certification, I will be in a situation in which I have read logs on everything I've read, and I have write logs on everything that I want to write. So then I can go ahead and commit the transaction and make those changes visible, and then start releasing my logs. Okay, and now, so that's then one way of realizing this protocol. Of course, with LStore or with even the indirection approach that we talked about, is that when I actually get a read log, when I actually want to write something, I can hold the read log to it, but I also can go ahead and write the new version, but mark that new version as uncommitted. You can also mark whether it's I write a new version in the tail page, but I mark it as uncommitted. So when other transactions come and see this, well, they know it's uncommitted, they can skip it and they can go to the previous committed version. So I can actually I can make my write written directly to the database, but just marking it that these things are not finalized. So whoever reader that comes along and notice them, they simply skip over it. But now the question is, can we make this a little bit more robust? And one thing to do is introducing this notion of update intent log. So as opposed to just naively get a shared log or a read log on a record that I'm planning to write, which does offer full concurrency because all the reader and writer can continue read the data, because everybody has shared logs and shared logs don't conflict with one another. But this idea of the update intent log, it says that I'm reading the record right now, but I'm planning to later change it. So an update intent log does not conflict with the shared log. So if there are transactions that are holding a read log, I can still request an update intent because I haven't changed anything. I'm just announcing my intent. And new transactions that come along while I'm holding my update intent log, and if they want to read the record, they can go ahead and still acquire shared log. So again, update intent lock won't interfere or won't conflict with any shared lock. However, if I'm holding an update intent lock, and if another transaction comes and wants to get an update intent lock, then there is a conflict. Then we cannot have two transactions having an update intent lock for the same record. So update intent lock is more restrictive than a shared lock, but is less restrictive than exclusive lock. Because when I had an exclusive lock, then even shared lock could not be granted. But when I'm holding an update intent lock, shared lock can be intended, but just no other update intent lock can be supported or cannot be granted. So what would be the benefits of having this update intent lock? Any thoughts?
Maybe you wouldn't have to reverse as many transactions that wouldn't be able to go through.
Yes, that's true. And so a little bit more specific, how I can avoid that? So what in particular I'm utilizing to achieve that point that you just mentioned? So that is another effect of it.
Well, if two transactions want to get an update or they have the update intent lock, then you know that there is going to be a conflict. So you have one wait rather than later finding out that we already updated. So like, let's roll back and then try to do the transaction.
Exactly. So it's because there's nothing really we can do with right-right conflict. Unless we now go inside the type of operation that is being done. For example, if you and I are simply incrementing a counter, then both update can go through simultaneously. You add one, I add one, the net effect of execution of our change is +2. But if these updates are arbitrary, it could be anything, then as soon as there's a right-right conflict, there's nothing we can do. For example, you may want to make it a price 12, I want to make it 15. Well, there's a conflict. There's no clear way of either one of them has to go through. Or if there's only one thing that is left to be purchased, well, only one of us can purchase that. So in general, right-right conflict is difficult to avoid or difficult to reconcile or to figure out how to resolve. And the only way is either you make one wait for the other, or you make one to be aborted in favor of another. So those are the mechanisms to be done. So now if we have this update intent lock, then we can now have much more control over detecting those right-right conflict early on, as opposed to wait for the certification, because otherwise they would have all got reblocks and well, everything looked good. But then they come to the certification phase and realize, oh, there's a right-right conflict. And now one of them needs to be aborted. As you mentioned, it will really help us to reduce, to identify these conflicts much earlier and be able to handle them or deal with them at an earlier stage. So now, can you see a parallel right now? So as we're moving forward, do you see a parallel between this and the indirection that we were talking about earlier today? How do we implement, for example, update intent lock into our indirection? The idea of update intent lock.
Well, I think it had to do with.
Go on.
I was going to say it had to do with the logical ID. There was kind of the uncommitted branch, and that was
exactly.
kind of a.
Yeah, so it's there. The moment that you write a new version of a record and you set your URID, the uncommitted read, that itself becomes an evidence that there is already an existing write that is happening. So in a sense, it can be implied as getting an update intent lock. I'm planning to update it, and I'm actually doing more. Not only I'm planning to update it, here is the version that I'm planning to write, And here is a pointer to it. If you wish to read it, go ahead and read it, but know that this is an uncommitted version. But also, if you write there, well, I'm already writing. So you either abort or you wait till I'm done. So all of that, with that basic simple fact of just maintaining or having the indirection to point to the latest uncommitted version, now we see we can actually implement a whole concurrency, or even start to look at a more sophisticated style of locking as well too, by that very simple data structure. And the interesting thing about that data structure is that since we're just dealing with these 8-byte pointers, we can do compare and swap, which is an atomic operation that's supported by the processor, by the hardware. So that means we don't actually need to hold any logical lock in the software. We can actually just do a lock-free, or in a more appropriate for database community, a latch-free design of implementing this concurrency protocol by really using compare and swap. And what compare and swap is in one atomic step, the processor compares two things, or it compares two things, and if that comparison is valid, then it changes one value. So what it means in this case, in order to do a compare and swap on a URID, initially, if the URID is set to null, meaning there are no outstanding updates, the compare and swap operation will be make sure that currently the URID is null, and if the URID is null, then make it point to this new record that I'm planning to write, or point it to this record that I have already written. So if that compare and swap operation is done atomically, and it is supported by the hardware, and if two people try to do a compare and swap on a URID that is set to null, only one of them will go through. And as soon as one will go through, the URID is no longer null. And so the other one will fail. So now we are updating a shared variable, one word size, 8-byte size, without actually holding any locks on it. Alternatively, we would have said, okay, I want to change this variable. We introduce a lock, first get a lock on it, and if that lock is available, then I go ahead and make that change. But right now, we are avoiding doing that by using that compare and swap operation. So that's something that is already, everything that we talked about so far can actually be implemented by just simply relying on that indirection column. And in fact, the way that the indirection column is designed right now, all this feature that we talked about can also be used in Elstar as well too, because that indirection column currently points to the latest version. That indirection column in Elstar can either be committed read or it can be uncommitted read. And one way to be able to figure out whether it's committed or uncommitted is that we could have a table or a transaction table in memory that simply maintains the state of each transaction, whether the transaction is committed or uncommitted. And what can be done is that if we had like a transaction ID of each transaction has a transaction ID, and in that transaction table, we could figure out whether this transaction has already committed or not, or keep the state of the state of that transaction. So what happens? A new transaction comes, and it writes a new record, adds it to the tail, and then makes the indirection point to this new tail record. And if that new tail record has a transaction ID which is uncommitted, then essentially the indirection is pointing to a URID. But if that transaction ID is committed, then the indirection is pointing to a committed read. So it can be derived whether it's a committed read or an uncommitted read. And where to store the transaction ID? We already had this column of a start time. So one way of storing the transaction ID is to, when you first write the record, the start time will be the transaction ID. And once the transaction is committed, at the commit time, it receives a time. And the start time later becomes that start time of the transaction. Because at the beginning, when we actually write the tail record, technically speaking, we don't know whether, even if this transaction is committed, let alone what time should be the starting point. Because the starting point of a record, of a valid record, should be from when the transaction is committed. At the commit time, we can only really get that starting time. So that's kind of a trick to get this two version indirection into that single version indirection that we have in Outstore to implement this protocol, for example, on top of it. So there was a lot there. I don't know if everybody, there was a bunch of intricacy there. You can sort of think about it, reflect on it, but this two-way indirection can be implemented cleverly using that single indirection that we have in Outstore because we have the tail pages. And you can do the entire thing latch-free. So there's no need to hold any locks for any of it. But just compare and swap, all the operation can be done without actually holding any locks. So now, kind of let's move forward is, well, one thing we've kind of noticed so far, you may have noticed, is that our writes are kind of optimistic. The writes are optimistic in a sense is that we start with either a shared lock or an update intent lock, and we assume by the time we get to the certification stage, then by the time we get to this stage, any outstanding reader is done, so we can certify and complete and commit the transaction. So that's an optimistic ground. We assume by the time I get to the certification stage, there's no outstanding reader, okay? But however, on the same token, if we pay attention, we see that for the readers, right from the start, we're getting the shared lock. So what does that mean? As a reader, I sort of assume that a more pessimistic approach saying that if I don't hold my shared lock right from the start, if I were to go ahead and read something, then there's a good chance that that would become invalidated before I end my transaction. So let me be pessimistic and let me hold my shared lock. So one way of looking at this is that writes are more optimistic, reads are more pessimistic. And now the question is there any opportunity to make the read also a bit more optimistic? So any thoughts? And perhaps maybe a step before that, when is it that optimism could potentially pay off?
When when there haven't been any writes in the meantime?
So when, yeah, so in other words is that if I were to do it pessimistically, the resource that I want to kind of acquire may not be available. But if I perhaps do it optimistically, by the time things will settle, there wouldn't have been any conflict. So in other words, this optimism could really become beneficial in those period of time where the rate of exclusion is high. So that means there are many exclusive locks, or there are many locked exclusive resources. So there could be a potential opportunity. So where would that be in this graph? Where is that region that there is an exclusion and there is a potential of optimistic read? Where would it be? In which phase?
the column in between?
Yeah, so the only place that really we're holding exclusive lock is that during the certification phase. So now the question is, how do we introduce optimism, especially optimistic read, in this exclusive region? In other words, we're going to allow the reader to read data even though there is a lock on the record. So now there's an interesting question. There's actually two versions of the record. During the certification, we still have the previously committed record, but the record that is just written is being certified. So we still have an uncommitted record. So which one do I read? Do I read the committed one or do I read the uncommitted one during this stage? I already know that in the previous stage, I was reading the committed version. But what do I read now in this region? And why?
The uncommitted one, just because it's in process of being committed, unless our certified log itself is going to abort. There's abort in some function, but I assume if we're trying to commit it already, it's going to be updated once we have exclusive lock.
Yeah, precisely. By the time I get to an exclusion or certification, on an optimistic ground, well, there's perhaps a very good chance that this is going to go through. So if I were to read this record, especially the uncommitted one, which I'm optimistic that they're actually going to become committed because the transaction who wrote it is undergoing a certification process, then it makes sense to read those. Of course, that read becomes an speculative read, meaning it's not like the read that we did with the shared lock that we were certain that it's going to be stable, nothing is going to happen to it. But if I were to read and sort of relax my exclusive lock and allow speculative read to happen in this phase, then what could happen is that the certification could fail, and any transaction who read from any transaction who did a speculative reads also might need to be aborted because they read the data that technically doesn't exist, and so they also need to be aborted. So they also need to hold the weight dependency because it is possible that the transaction who read the data that was being certified, in fact, get to commit before the certification ends. So now there must be a weight dependency also added, is that you would only allow a transaction to commit if it has no weight dependency on any unconcurrent transaction. And if all its weight dependencies, all the transactions from which it is speculatively have read from, they all have now fully certified and committed, there is no dependency, so a transaction can proceed. But if any of those transactions who speculatively was read from actually fail and abort, well, then this transaction needs to abort. Or if there is one that still hasn't been certified and is still in the process of certification, and the speculative read transaction is kind of done, just needs to kind of complete, it cannot be allowed to pass through until that transaction that was read from also finishes its certification. So it creates a weight dependency, and it also it creates the potential of having cascading aborts, because if I read from a transaction that was aborted, well, I need to abort, and potentially any other transaction who read from me speculatively also must abort. So we get into that cascading of abort situation. So we relax our exclusive lock, we allow speculative read, and in a sense increase the optimism. And the optimism was exactly what was mentioned, is that it is there is an optimism because we're reading from a transaction that is already doing its certification. So, well, maybe there's a good chance that it will complete. It's no guarantee, but maybe there is a chance. There's a much better chance. And so now it introduced optimism both for reads and having optimism also for writes, as we had already described it. And this speculative read, again, can easily be also implemented with that indirection, because from the indirection, we can get to the latest URID, we get to the latest tail record, and we can figure out this tail record is being uncommitted. We can also, in that transaction table that I mentioned, we could have more states in it. Is that we could have a state is that is ongoing, state that is certifying, and a state that is committed, and of course, a state that is aborted. So we could have multiple states, and if a tail record is written by a transaction that is ongoing, well, then it doesn't have an exclusive lock anyway. It only has a shared lock. But if it is a transaction that it's now is on a certification phase, then I may choose to read that uncommitted tail record, and well, then just hold the dependency on that transaction from which I'm reading from. So again, this can be implemented without introducing a lock manager, without introducing a lock structure. It can be really implemented entirely with that indirection, and also can easily be implemented in LSTOR without introducing yet another structure. Any questions?
Since the certified phase is supposed to be very short, why can't you wait it? Like wait till the shrinking phase after all the exclusive locks on write are released, and then you are guaranteed that they're all like updated and correct.
Well, when we're dealing with concurrency and locking, the most important goal is to reduce wait time. And so we don't want to stall any, because the moment you wait, you're essentially stalling your processor. Essentially, potentially a CPU is going offline. And so you lose parallelism and you will lose performance. So ideal scenario, 0 wait time. And this wait time could become extended as well. For example, if a transaction read a whole bunch of records and it's now wants to certify those, and for each of those records that is read, there is a whole bunch of other transactions who are reading those records and they're still active. So when it requests an exclusive lock for a particular record that other transactions are still reading, well, they have to wait for those to finish. So it could be the case that certification, although it could be just as fast as just acquiring a bunch of logs, each of those logs have a weight to it. And so they're not granted right away. So now we could potentially be waiting for a while for that certification to end, just because it's just, we're simply waiting for logs. We're not waiting for anything else. We're just waiting for logs. And so that now motivates is that, well, can I do a little bit better while I'm doing all these waits? Maybe I can get a bunch of other transactions started too, and hoping that well, these will certify and everything will be fine. And why wait? Let's get more transactions get started. Does that answer your question?
Yep.
Okay, sounds good. Again, then that's an important. That's a very important point. So the other thing is we've kind of already alluded to is this whole notion of blocking and non-blocking. Blocking is basically getting a lock, and if that lock is not available, for example, if I'm requesting a read lock on a record that is another transaction is certifying, which already holds exclusive lock to it, well, I can't even get my read lock. And so I may have to simply wait. And how long I wait, well, it affects the latency of that execution or just the overall runtime. The other one is one way to implement these. Another way is kind of say, well, I'm not going to wait. If something is not available, I can just drop it and abort it. But if I do want to wait, one way is to kind of keeping a counter and keeping a queue. Is essentially saying that, well, I want to get an exclusive lock, for example, and right now there is 10 outstanding readers. Well, I guess I'll just wait till this 10 outstanding reader to end. Then I'll go ahead and I'll take the next thing in a queue, which is now an exclusive lock. So that the exclusive lock is taken once those 10 outstanding reader are completed. So that's the notion of blocking. And I think it is useful, especially if the transaction was, it was very expensive one, it's already gone through so much execution and processing and reading data perhaps from disk and so on, and maybe some complicated analysis, then blocking does make sense, is that we don't want to just throw away all those work. But what we observe in sort of workloads, especially transactional workload like sales, these workloads are, each transaction are rather short and is done really quickly. In fact, just doing a context switches, it could be 20–30% of the cost of execution of a whole transaction, just one single context switch done by the operating system. So we even avoid context switches, meaning that if you have 20 physical threads, even with hyper-threading, or we have 50 physical threads, then we at most run 50 concurrent transactions. Also assuming that we don't need to hit the disk, all the data that we need is in main memory. So we will instantiate one transaction, concurrent transaction for every available core or physical thread. So that means there's never going to be context switches among threads. We're just one thread continuously just grabbing another transaction and just executing one transaction of another. We know in a normal traditional databases, especially with a lot of disk in this disk involved, if we had two physical threads, we may have instantiated 30, 40, 100 concurrent transactions. And those two physical threads kept switching between these concurrent transactions to be able to kind of hide the latency of the disk accesses and so forth. But when we already eliminated the disk accesses, assuming the memory is large and at least most of the transactional data fits in memory, so there's no really delay. And so we want to avoid context switches because now context switches becomes very expensive. And at the same token, aborts now are becoming much cheaper. So then it makes sense to just drop something and abort, and let's not even wait for anything. If something's not available, simply just abort it and move on. And we can retry it later. And so again, that introduces yet another interesting dimension to the concurrency protocol, is that we want to be able, whether maybe for some transaction it makes sense to block, and for some other transaction makes sense to do non-blocking. So have the flexibility, if the concurrency protocol is flexible enough to support both, well, that's great. In fact, so what we show in the 2VCC, so I've kind of put a link to the paper on the website as well, is that we looked at the ability to do blocking, non-blocking, pessimistic, optimistic, and all of these kind of what we've been discussing at the same time. So some transaction could be blocking, some transaction could be non-blocking, some transaction could be speculatively read, some transaction says, no, we don't want a speculative read. All of that can coexist without interfering with one another. And all of them entirely can actually be implemented around the indirection, interestingly. So that becomes a little bit more elaborated, kind of outside the scope of this course, or at least these lectures, but all of those are important. So we want to be able to have a flexible model that allows us to fine-tune the concurrency control based on the behavior, based on the kind of the workload that presently is being observed. And the workload can also change, maybe on a weekly basis or hourly basis or daily basis. And if the protocol can sort of adapt itself, then it would be interesting. In fact, if some of you had mentioned in some of the earlier lecture, can be used kind of AI and deep learning or machine learning or other kind of statistical analysis to figure out how do we adopt these protocol. And well, if a protocol is flexible enough that can be able to be configured at the same time with different kind of parameters, and now if you accompany some learning around it, then you can create this protocol really dynamic as the database is handling transactions, sort of operating in real time. So fine-tuning the protocol in real time based on statistics that we're getting from the workload. Any questions? Okay. So experimental analysis, I think is something that I think it's important. And some of you did it for your milestone, which is great. And I think we should do it even more for the remaining milestones. And I kind of, next time I will show more. I mean, some of these settings I've already shown you in earlier slides, I'm not repeating it. But in the, especially for the next class, we're going to be a lot more detail on the experimental analysis. But here again is one set of analysis. Again, it's important to first specify what kind of workload we're running, what is the kind of machine that we're running, and so forth and so forth. And here, and also the kind of experiment. So the experiments that we're running here is we have changing the number of parallel transactions from 1 to 64. And then on the y-axis, kind of showing execution of updates in second. And these are done in an actual database. So it's not just a prototype. This is implemented in a commercial database. And what we're comparing with is the single version, which is your classical 2PL, and then the multi version, which is the 2VCC that we've been discussing. And so what's really apparent is that we increase the contention, and by increasing the number of parallel transactions, essentially we're increasing the contention because now there's more opportunity of conflict. With a single version, especially with 2PL, with all the locking that is happening, once the contention becomes large enough, there's a tremendous gap between single version and multi-version. And that's sort of captured in this graph. And so that's kind of validating what we've been discussing. Kind of looking at a little bit more detail, we say, okay, well, why are we getting these benefits? So sure, we're getting the benefit, but can we look at a little bit more data of what's happening under the hood? And this was, again, the question was also mentioned, why don't we wait? And that's such an important parameter because, so here we're kind of looking at the deadlock, we're looking at the lock weights, number of lock weights, and the actual waiting time. So this means how many times a deadlock was identified. This means how many times a lock wait request was issued. And this means, well, how long in total, how much time was spent just waiting for locks. It's possible that we have thousands and thousands of locks requests being issued, but all of them will be granted after 1 millisecond. So it's important to count how many lock weights was issued, but it's also equally important to figure out, well, how long each of those end up causing, creating wait time. And again, as not as surprising, as you increase the number of parallel transactions, as you increase the contention, all of these numbers just shoots up. And these are the reason that we get that increase in the runtime. And these are the reasons is to avoid the lock wait time. And here actually the protocol that is implemented here, the variant that is implemented here is without blocking. So if something is not available, it's simply just drop. So there's nothing is being waited on. And interestingly, if you do implement a two-phase locking without waiting, you also dropping deadlock. There's no way to have deadlock, because the only way you have a deadlock is that if you wait for something and you wait for your friend and your friend is waiting for you and you're both stuck because thinking, well, the other one's going to come while the other one is waiting for you. But if there's no wait, well, there's never ever possibility to get deadlock. So having this non-blocking not only drops lock wait, but it also avoids any deadlock. And deadlock is not easy to detect. And the reason it's not too easy to detect is, well, you constantly have to create. So if you remember, we talked about that dependency graph. So we can always create a dependency graph, and if we see cycle in that dependency graph, we can figure out that there is a deadlock happening. But now constructing a dependency graph and constantly updating a dependency graph as we execute more operations of this transaction, it's a very costly thing. And so one thing, you have to maintain that graph, and you also have to run your algorithm to see if there's any cycle in it. So maintenance of the dependency graph as a whole cost on its own, and the frequency that we run our deadlock algorithm or checking for cycle in the graph itself is another cost. So maintaining or detecting deadlock is often is a complicated piece of code, and it's also expensive. So when we talk about deadlock, we have detection mechanism, we also have prevention mechanism. So not ever waiting for a log, what's a preventive measure? Well, if you never wait, there's never a possibility of a deadlock. But a detection mechanism was, well, we draw a dependency graph and see who's waiting for whom. And if you start seeing cycles, that one transaction is waiting for another transaction, but that transaction is also waiting for this transaction, then, well, we can say, well, there is a deadlock. So that's another important kind of looking at not only just numbers, but look at statistics to kind of say, does it make sense, these numbers that I'm getting? So that's equally important, because it is often, there may be bugs or there may be potential optimization opportunity. There's a lot that could happen the moment we go one step deeper to see why is it that we're getting these results. So that's important. Again, this was interesting that some of you did the analysis and had these really nice graphs, but not all of you have kind of looked at every data point to make sure, well, does this data point that I'm getting, does it make sense? Or why is it that I'm getting it? Why is it that I'm getting this performance profile? So that's equally important, or maybe perhaps even more important. But once you do the analysis, once you draw the graph, then say, okay, why? Justify it. And then perhaps look at, can you improve it, or can you eliminate any flaw that you identify, and so forth. So they're essential. Okay, any question? Well, let's kind of look at the state of databases as it is right now, or one vision of the database. And we're going to play with this vision a little bit more and kind of develop it further together as well for the remaining of the month. So what we talked about so far, a kind of a recap, is that we had this read optimized data, and then we have this write optimized, you have the OLTP, and then we have OLAP. And periodically the data from the transaction gets pushed into the OLAP. So essentially this data is always kind of stale. So our analysis is always on the old data. And then the question was to have this hybrid model, this HTAB model, and sort of the L store was a solution to this. So creating a single engine that can do OLTP and OLAP simultaneously. without the need of maintaining two different databases, without the need of shipping data periodically, and without the need of limiting our analysis and report to stale data. But now the next question is, well, if this data becomes too big, can I partition it? Can I go from this centralized view? So far, both in our implementation and both in our mindset, we assume we have everything is in a single machine. But what if the data cannot be done in a single machine? Or what if the execution cannot be done in a single machine? And so we really need to partition our data across many machines within a data center. And the compute is moving toward that utility form, is that we will have this big cloud company like Amazon, Google, and Microsoft, and hopefully others becoming major player, that you simply, in the same way that you buy your electricity from, you buy your compute needs. And so, and if you buy your electricity and you want, and you use a lot of electricity, for example, then logically you're just buying this whole bunch of electricity, but physically, if you're a cloud provider and you're running databases in your cloud, it's not that you can construct this one single powerful machine and give it to this very demanding user. Is that you may give the abstraction, or that the user is kind of dealing with a central setting of a single machine, but in the back end or in the background, you may actually have many machines working together in a distributed way to support that demand. So it's really important to be able to scale into many machines. So that becomes the next central problem. And one way of doing it is to kind of partition your data. So as opposed to have all your data in one machine, you kind of maybe each, based on the geographic region, you can kind of do data partitioning. So now if you are, instead of having a single database, you kind of partition it across multiple machines, then if the transaction that you're executing only falls within one of these partitions, then things are great. But if a transaction that I want to run, it falls into two of these partitions, well, remember that we have to make sure that our execution is atomic, meaning that either both are done, both segments are done, or none are done. So now we need this additional code, in addition to our concurrency protocol, to make sure that concurrent transactions are ordered correctly within a single partition on a single machine. Now we have to make sure that that ordering that happens in one machine is, in a sense, is consistent with the ordering that happens in another machine. And the only way that a single transaction is committed or completed is that not only it successful on one, but it's also successful on both. And you could have serializability issue, is that if I'm just doing concurrency control blindly in each of these independently, I may become a scheduled in which transaction T1 is followed by transaction T2, which is great. From the perspective of this node, that's serializable, so that segment is completed. And if I just do blindly do local concurrency control here, and let's say these transaction T1 and T2 hit the same data on both machines, I may come up with a different serial order of first executing T2 followed by T1. And locally, I would say, okay, this is also done. And then I could even have an agreement protocol saying that both of them said at the same time, well, yes, we're both done, we're good to go. And I then reach a false agreement, that is, or an agreement that doesn't result in serializability, because part of the transaction was done T1 followed by T2. The other one is the reverse. So now it becomes more interesting. So the moment we go distributed data across our partition, and I want to be able to do cross-partition transaction or multi-partition transaction, then not only you have to make sure concurrency within the same database, within the same machine is serializable, but also these are consistent. It actually has to be the same ordering. It has to be a consistent ordering. And also reaching an agreement that they all succeeded. So that becomes an interesting sort of next step. The other thing that I think becomes interesting, kind of even taking this stuff one step further, is right now, even with this partition model, with this distributed model, what we have a single entity that everyone trusts. Let's say the bank or the government. And so there is a single bank, there's a single authority that decides the fate of every transaction, or also decides and remembers each transaction. So for example, your favorite bank, whether you buy stuff from Starbucks, McDonald's, or whatever, you exchange money with your friends, you go through this bank. And the ledger that that bank maintains is the ground truth. So that bank says what was done, and 6 months from now, the only way that to prove what was actually a transaction that taken place, the only real proof is go to the bank and says, okay, can I look at my previous statement and to see whether that transaction was taken place? And if the bank says, well, sorry, we no longer have that statement, there's really nothing you can do. Or if the bank says, oh, I cannot show you that statement anymore for whatever reason, well, we have no more proof that this was actually taken place. And so there is an implicit trust in that central authority. And it might be the case that it's not that this central authority is necessarily malicious, but simply becomes a catastrophic failure, and all their server goes down for whatever reason, because of a major earthquake or a hurricane. And well, this data no longer available, and potentially all the transaction that was, or the ledger that I was maintaining is gone. So there is the notion of trust, and also in terms of assuming there is no bad intent. The intention is always good. The assumption the intention is always good, and also assuming that there's always availability. And even if the things goes down, maybe any unavailability will be a very small, short period of time. But generally is always available. So now the next question is, what if we, instead of having a single authority that maintains that ledger, a single authority that maintains that database, what if each of these actors or each of these participants, or at least some of them, will maintain a ledger of their own? And all of these ledgers are of identical copy. And each of those ledgers internally could be a distributed database internally, or we're not really concerned, kind of one higher abstraction. So now, instead of having a single entity to hold the data, we have 4 different entities. So we'll say 2 individual and 2 corporation. They each maintain a copy of the ledger, which means for a transaction to be considered finalized and committed, is if that the majority, here in this case, majority of these 4 people, 3 out of 4, endorse it. And as long as the majority endorses, then we are able to withstand or tolerate a failure of minority. And that failure, whether it's malicious or non-malicious, doesn't matter for now, as we can handle that failure. So through partitioning, we get scale. Through replication, we get availability. The data is always available. But also we get tolerance and resiliency to crashes and malicious intent. Of course, for the partitioning, we can do things at the larger scale, but we have to pay the cost of agreement, and there is some new intricacy. So there are some costs. When you talk about replication, there's even more costs now, because not only we need to maintain a single database, everything that we talked about was for a single database, but now we have to make sure that not only this ordering that I came up in this partition is consistent with that partition, but the ordering, the combined ordering that I came in this among these two, this is one replica. In every replica is also consistent. So the concurrency control said I get a serial consistent order within a single machine. The distributed transaction, so the central transaction said a serial order in the same machine. A distributed transaction says a consistent serial order across machine. And now with the replication is that consistent ordering among machines across all replicas. So kind of incrementally, we are building on that. Concurrency, agreement, and consensus. Consensus on that all the replica. Agreement in a sense that every segment of the transaction was succeeded. Some of these consensus and agreement can be used interchangeably often, and it is used, but that's one terminology to adopt. And this whole notion of blockchain, and I think it's the excitement around blockchain, it really falls into this final picture. And we're going to talk about this a little bit more, I think, toward the end of February. I hope to can spend at least maybe 1 or 2 lectures to kind of look into that kind of interesting transactional problem, just from the transactional perspective, looking at that as well too. And of course, so now our data keeper become this replicated chain. And so essentially we have a ledger of a chain. Everybody have their own ledger. And for anything to agree or anything to be considered committed or finalized needs endorsement. So it's not just a single entity making the shot. Assuming that all the computation is happening in the cloud, and what happens is we're trusting the cloud provider to do the computation correctly. Now the question is, can we introduce a level of fault tolerance between the user and the cloud to kind of overlook whatever that the cloud is doing, the cloud provider is doing is correct. So essentially, seeing as a blockchain as a layer that brings reliability to otherwise potentially unreliable infrastructure, unreliable in a sense that you don't necessarily want to trust it. And so that's another interesting sort of instantiation of the same problem. It's not exactly a typical use case, but it's another interesting use case as kind of using a blockchain as a trusted middleware that allows bring reliability to any unreliable infrastructure. And that's something we've been looking at for some time now as well too. And this becomes even more interesting if you say, well, if my computation is not even within a single data center or within a single cloud, it spans multiple clouds, and using this layer as a way of consolidating and as a way of orchestrating your execution, your workload across cloud provider with fault tolerance. So again, that's another sort of, I think, very interesting direction that we will probably see in the coming years. And with that, wish everybody a wonderful day.